Hey guys! In my last video about selenium, I showed you the reaction between selenium and oxygen, which forms selenium dioxide. This time let's try to collect this substance. I placed selenium in a quartz tube within a round bottom flask to retain most of the selenium dioxide formed. Along with selenium dioxide, red selenium accumulates in the flask as it condenses from the black selenium vapor. The white coating inside the flask is selenium dioxide. If we pour it out, we'll see a red powder due to the presence of red selenium. The selenium dioxide you see now appears as white, needle-like crystals. Selenium dioxide obtained by burning selenium easily dissolves in water, forming a transparent acidic solution known as Selenic Acid. Red selenium is insoluble in water and can be filtered out easily. Thus we have obtained a solution of Selenic acid. Pure Selenic acid forms snow-white crystals. Selenic acid is a typical weak acid, much more easily reduced to selenium than sulfuric acid is reduced to sulfur. By boiling selenic acid with concentrated hydrogen peroxide and passing oxygen, selenic acid can be oxidized to selenic acid. For ordinary distillation, selenic acid concentrations of up to 80% can be achieved. However, to obtain crystalline pure selenic acid, we need to remove all the remaining water under vacuum. To create a vacuum in the system, we'll use a vacuum pump connected in series through a Bunsen flask filled with a mixture of silicon dioxide and potassium hydroxide. The tube attached to the left neck of the flask is a thin capillary tube, which prevents explosive boiling. You can test your capillary tube. When air passes through the correct capillary into diapholyfer, we can observe individual bubbles as shown in this footage. If the capillary is faulty instead of individual bubbles, you will see vigorous boiling like this. So let's get started. I'll create a vacuum, adjust the oxygen supply for the capillary, and turn on the heating. Vacuum distillation not only helps separate azeotropic mixtures, but also prevents the substance from decomposing at its boiling point. The temperature at which water is distilled under these conditions ranges from 40 to 50 degrees Celsius. After water has stopped flowing into the receiving flask for an extended period, the vacuum distillation can be considered complete. Now I pour the resulting syrupy liquid, which is pure selenic acid, into a flask. To obtain crystalline selenic acid, we need seed crystals of selenic acid. We will obtain them through freezing. I take a few drops of selenic acid in a test tube. Then take a small beaker, pour a small amount of acetone into it, and add a few pieces of dry ice. Once the temperature settles around -70 degrees, I lower the test tube with a few drops of selenic acid into this cryogen. The crystals formed through freezing will adhere to a glass rod, which can then be touched with liquid selenic acid. This will initiate the immediate formation of crystalline selenic acid. Thus we have obtained pure crystalline selenic acid. Now let's move on to its chemical properties. Selenic acid crystals are extremely hygroscopic and deliquesce within minutes when exposed to air. Our first reaction will be the dissolution of gold. As far as I know, selenic acid is the only acid capable of dissolving gold on its own. There is a small possibility that perchloric acid can dissolve gold too, but I haven't tested it yet. Selenic acid needs to be heated to dissolve gold, so let's heat it up. The dissolution of gold in selenic acid results in a yellow-orange solution of gold selenate. This is a rather unique chemical reaction. The metal dissolves in the acid without any gas being released. This reaction has no practical significance, since selenic acid as a solvent is a rather expensive reagent, and when gold is reduced from it, selenium will also always be reduced. When heated, silver also dissolves in selenic acid, forming silver selenate. Initially, black silver oxide is formed, which subsequently dissolves in the acid. So let's observe how selenic acid burns paper. I'll melt some selenic acid crystals so we can pipette it. Similar reactions with selenic acid also result in the formation of red selenium. Now I'll show you the reaction between selenic acid and sugar, but before that, let me remind you how sugar reacts with anhydrous sulfuric acid. Unlike sulfuric acid, selenic acid takes much longer to carbonize sugar. Charring with selenic acid, like most other reactions involving it, leaves behind noticeable amounts of red selenium. Let's use a thermal imager to compare the temperature during the dissolution of selenic acid and sulfuric acid in water. The maximum recorded temperature when dissolving selenic acid is about 80 degrees. Obviously, sulfuric acid provides a greater thermal effect, with a temperature during dissolution always exceeding 100 degrees. Sulfuric acid easily oxidizes potassium iodide to free iodine, but when reacting with potassium bromide, it forms hydrogen bromide, and only a small amount of elemental bromine is released, giving a yellowish color to the potassium bromide powder. Now let's compare these two reactions with selenic acid. The reaction with selenic acid produces a significant amount of iodine, and the reaction proceeds much faster. Let's take a closer look in slow motion. Now observe how selenic acid readily forms elemental bromine from potassium bromide. Like sulfuric acid, copper dissolves when heated in selenic acid, forming a blue solution of copper selenate. This is what a solid copper selenate salt looks like. Both salts precipitate when interacting with a solution of barium chloride. Visually, the reactions with hydrogen hydrate and potassium iodide are similar. Let me know in the comments which reaction you think would help distinguish copper selenate from copper sulfate. An interesting reaction occurs between selenic acid and a solution of tin 2 chloride in hydrochloric acid. Initially, red selenium is formed, but with further addition, black selenium is produced, accompanied by the release of gas bubbles. This is because selenic acid readily reacts with hydrochloric acid, resulting in significant heating, causing the red selenium to turn black. In this reaction between selenic acid and hydrochloric acid, the liberated chlorine causes the hydrochloric acid to turn yellow-green. Similarly to the reaction of magnesium with sulfuric acid, I would like to present the reaction of magnesium with selenic acid. Note, in this reaction, magnesium reacts with selenic acid to form red selenium. Sodium and potassium also react with selenic acid to form selenium and the selenite salt. Unlike the conc reaction of samarium powder with sulfuric acid, the reaction with selenic acid proceeds much more violently. Now I'll show you a reaction between selenic acid and phosphorus. I'll melt a small amount of selenic acid crystals in a test tube and add a small piece of white phosphorus. Let's repeat this reaction using even smaller amounts of the starting materials. Now let's add a drop of anhydrous hydrazine to the selenic acid crystals. As you can see, the characteristic blue flame of selenium is observed. And here is the reverse. I'll drop selenic acid into anhydrous hydrazine. These were some interesting reactions I prepared for you in this video about selenic acid. Be sure to leave comments and if possible consider becoming my patron. Thanks to your support I can continue creating unique chemical content. Thanks for watching guys, and a huge thank you to my patrons. See you in the next video.